In this lesson, we're going to learn how to draw what are called electron dot structures. Then we're going to use those electron dot structures to figure out how many single covalent bonds an element needs to form in order to have a full outer shell. So what we know is that valence electrons are found in the element's highest shell. Valence electrons are so important because they're involved in the formation of the different types of chemical bonds. So elements generally want to form chemical bonds in order to change their configurations to be similar to the noble gases. They want to try to obtain a full outer shell generally. That means having 8 valence electrons, and we refer to that as following the octet rule. What you need to know moving forward is the trend for valence electrons on the periodic table. All of the elements in group 1, they all have 1 valence electron. All of the elements in group 2 all have 2. You're skipping the transition metals, the D block, group 13-3, 14-4, 15-5, 16-6, 17-7, and then all of the noble gases have 8 valence electrons except helium. Helium has 2. So you have to know this trend in order to quickly answer the problems that we're going to be solving in the upcoming lessons. So what an electron dot structure is, it's a way to kind of represent the valence electrons that an element has by placing them around the element symbol as dots. There's different applications for electron dot structures. You can use them to model what's happening in an ionic bond, in a covalent bond, but we're going to kind of just use them to figure out how many single covalent bonds an element needs to form in order to have that full outer shell. So to draw an electron dot structure, you determine the number of valence electrons, you write the element's symbol, then you place the valence electrons as dots around the symbol. So let's go through and look at nitrogen. Nitrogen has a total of 5 valence electrons. I know that because nitrogen is in group 15 on the periodic table. So I write nitrogen's symbol. Think of the symbol as having 4 sides: a top side, a right-hand side, a bottom side, and then a left-hand side. What I'm going to do is I'm going to start on the top and place those dots clockwise around the symbol. I can only start to put 2 dots on the same side once all 4 sides have a dot. So 5 valence electrons, 1, 2, 3, 4, 5. I stop and I'm done. All right, so once you have the electron dot structure, you can then analyze it to figure out how many electron pairs and unpaired electrons there are. So 2 electrons on the same side counts as a single electron pair. An electron that's by itself counts as a single unpaired electron. So nitrogen has 1 electron pair, and it has 3 unpaired electrons total. So go through complete numbers 1 and 2 for the check for understanding slide. So sulfur has a total of 6 valence electrons. It's in group 16. So I write sulfur, 1, 2, 3, 4, 5, 6, and then I stop. 2 electron pairs, 2 unpaired electrons. Bromine, group 17, it's a halogen, so 7 valence electrons total. 1, 2, 3, 4, 5, 6, 7. I stop. 3 electron pairs and 1 unpaired electron. What we know about a covalent bond is it's formed when nonmetals share electrons with each other in order to obtain a full outer shell. What we now need to do moving forward is understand that in a single covalent bond between 2 nonmetals, it's 2 valence electrons that are being shared back and forth. So in a single covalent bond is formed between 2 nonmetals, 2 valence electrons are being shared back and forth. We can use an electron dot structure to determine how many single covalent bonds an element needs to form to have that full octet. So the number of single covalent bonds an element needs to form to have that full octet is equal to the number of unpaired electrons in the electron dot structure. So for example, fluorine has 3 electron pairs, but it has 1 unpaired electron, and what that tells us is that each individual fluorine atom would need to make 1 single covalent bond in order to reach an octet, in order to have a full outer shell. So let's kind of look at this, visualize it using electron dot structures. So here's two individual fluorine atoms, and when they're by themselves, they each have 7 valence electrons. But what they're going to do is those two fluorines, if they form a single covalent bond and they share their unpaired electrons, we could see on the right-hand side that both of those fluorines now have 8 valence electrons around them. Both of them now have a full octet, and they're now going to be stable. In the next few kind of lessons, we'll talk about what are called Lewis structures. And in Lewis structures, we'll talk about bonding versus non-bonding pairs in molecules. But a bonding pair is when you have the 2 electrons being shared back and forth. And what we'll talk about in the next unit is how those bonding pairs can be represented by drawing a line between the 2 elements in the molecule. But for right now, just understand how to draw a single electron dot structure, determine the number of electron pairs and unpaired electrons to then determine how many bonds it would need to form to have that full octet. So what I want you to do is numbers 1 and 2 for check for understanding. So carbon has 4 valence electrons, so its dot structure looks something like this. Since it has 4 unpaired electrons, it would need to form 4 single covalent bonds in order to have a full octet. How many electrons are shared by 2 atoms to create a single covalent bond? In a single covalent bond, it's 2 valence electrons being shared back and forth. We'll also add double and triple bonds later on, but for right now, when a single covalent bond is being formed, it's 2 valence electrons being shared back and forth. This slide is important because it's going to help you understand a certain property of hydrogen that's going to make it an exception when we're drawing Lewis structures for molecules in the next few lessons. So go through and solve numbers 1 through 4. So hydrogen has 1 valence electron, so its electron dot structure looks something like this. There's one unpaired electron, and there's 0 electron pairs. So since it has 1 unpaired electron, it only needs to form 1 single covalent bond to be stable. When it forms that 1 single covalent bond with another element, it's going to end up having 2 valence electrons to make it stable. So hydrogen is an exception to the octet rule. How many valence electrons does it need to be stable? It's going to need 2 valence electrons to be stable. Hydrogen's goal in covalent bonding is it's trying to be similar to helium that has those 2 valence electrons in its highest shell. So when we draw Lewis structures, what you're going to find is hydrogen is an exception. Once it forms a single covalent bond and it has 2 valence electrons, it's going to be happy and stable, and we don't add anything else to it.